This is part 2 of lecture 1. We're going to be going over an introduction to Zybooks, Java, and in general algorithms. But first, let me introduce you to Bill. So Bill is having trouble in class. He's having trouble getting programming assignment 0 and programming assignment 1 done. But rather than scheduling a meeting with the TA or the instructor, Bill asks Sally for help. Seems like a logical thing to do. Bill did read the academic honor policy, but nobody will probably notice, and it's not that big a deal. So he just talks to Sally, and she gives him a few lines of code to use, and that fixes the problem, and he gets his homework done. Well, Bill is completely wrong. The tool that we use catches the code similarity, and Bill and Sally both failed the course and have a permanent record with Vanderbilt academics. So don't be Bill, don't be Sally. Both cases end up in failure. Don't ask for help, don't give help. If you need any help completing the programming assignments or the Zybooks activities, please schedule a time with the TA or email myself and set up a time to meet with me. So we've already talked about that Zybooks is going to be our primary book for this semester. Zybooks houses the weekly Zys, and in general, it's an active learning environment that has a lot less text, but more interactive exercises. It'll, in general, coincide with our lectures each week, and we will cover throughout this month, summer, first half semester, 10 to 11 chapters. So today we're going to demo Zybooks learning activities to make sure that everyone understands how to access and complete a Zybook activity. In part 3, we'll be going over a Zylab, also part of Zybooks. All the Zylabs are housed in Chapter 12. The Zylabs are where you will find the programming assignments. It also houses an interactive testing environment. Typically, you will be assigned 3 programming assignments per week, and each programming assignment will be between 2 and 4 exercises. So plan for a significant amount of time set aside to work on programming assignments each week. As I said previously, roughly 9 to 20 hours. Each chapter in the Zybook consists of information and participation activities along with challenge activities. They are more or less what they sound like. A participation activity is going to be, in general, more simple, and it's going to almost be like a reading check question. The challenge activity is going to be something that tends to put into practice what you have been reading. The grading process, in this case, is all about completion. If you complete more than or 90%, so greater than or equal to 90% of the Zybook activity, you get 100. Anything less than 90%, and you get the grade that is shown in Zybooks. It should take you between 1 to 3 hours a day, or 6 to 9 hours a week, to complete all of the Zy learning activities each week. So again, plan for that. Plan for a good bit of time each day set aside to complete Zybook activities. You may get it done much faster. You may get it done. It may take you a little bit more time. So there will be no late submissions of Zybook activities, and the free late days that you have cannot be applied to Zybooks. Now, that being said, and I misspoke about this in the lecture 1.1. I believe I said there were 3 free Zybooks or three Zybook activities that will be dropped. That's incorrect. There will be 2 Zys dropped. So if you are late turning in or completing a Zy activity, then that'll be a 0. However, a 0, if that's the lowest grade you have, will be dropped. So just keep that in your mind. You have 2 Zys that will be dropped. So we're going to go through a quick demo of Zybook activities. We're going to look at this activity from Chapter 1 regarding syntax errors and regarding compiler error messages, and then we're going to look at a challenge activity, which also gets into more syntax errors. Then we're going to briefly look at how to check your progress and to download a completion report so that you can have a record of what you completed if you wish. So each Zybook activity is going to look similar to this. You'll have information to read, and then there'll be figures and various things to help explain the concepts. Here we're talking about the compiler reporting a syntax error to the user, the programmer. So in this case, the programmer has left off the semicolon at the end of the statement in line 4. So the compiler generates an error, and in this case the compiler hits the nail on the head. It says, hey, you left out a semicolon, and it's in line 4. So the compiler did a great job here. So let's go down here to participation activity 1.71. There we go. So system.out.print numdogs, period. No error? Nope. Okay, the statement ends with a semicolon, not a period. All right. We needed a plus sign in between the two. The S in system should be capitalized. There's no quotation marks at the end. So pause right there. The double slash marks, we'll talk about that later, but that is an escape statement. Numdogs, the N in numdogs should be lowercase. There should be a semicolon after the first statement. And then finally, it should be system.out.print. So let's look on down at participation activity 1.72. So this is an interactive activity, so we'll set the speed at normal speed. Step 1, it shows the compiler processing the code. It saw a statement with error, but it didn't generate an error message immediately. It generated it and said that it was on line 5. If you find that the compiler generates an error message on line 5, then that means there is an error in your code at or before line 5. That's what this participation activity is showing. Now, right there is an option. You could have played that participation activity at 2 times speed if you understood the concept and wanted to move forward more quickly. So now let's go down to look at the challenge activity. So challenge activity 1.71. So what this wants us to do is input this code into the development environment and to correct the syntax errors that exist. Indentation is important because improper indentation would result in style points being lost if this were a programming assignment. So the first error is this should be print line. Next, there was a period here. It should have been a semicolon. And finally, to combine two items, the plus operator should be used in the print line statement. So there we go. We passed all the tests. So at this point, this challenge activity is complete. You can see that it says the test passed, all tests passed. So now let's look at how to check your progress. So when you log into the Zybooks platform and you go into the CS1101 Programming and Problem Solving home, there should be a panel on the right hand side which you can select reporting. When you select reporting, it shows each section, each chapter of the book. So here we have expanded chapter 1. So it says that chapter 1 is 11% complete based on what we just did in the little show and tell activity a moment ago. So the challenge activities are 11% complete and the participation activities are 8% complete for all of chapter 1. For 1.7 specifically, we did one of the two challenge activities, and apparently we did 42% of the participation activities. Now you can expand that to see exactly what was completed and what was not. So we did everything to do with syntax errors as far as participation activities. We did the compiler error message, and we did the basic syntax error challenge activity. Now, if you were to check this box for just this one section of chapter 1, or you could check the box for all of chapter 1, the download report would be highlighted, and you could download a report of all of the completed participation and challenge activities. Now, nothing has to be submitted on Brightspace for Zybook activities or for Zybook labs, the programming activities. All of those will be graded directly by the instructors and the TAs in the Zybooks platform. So once you have completed it here, it will be graded in this platform, and then we will input your grade to Brightspace. So you do not need to download the report and submit that to Brightspace. There's nothing to be submitted. Everything is done once you've completed it in this platform. So moving on from our introduction to Zybooks, let's talk about algorithms. So computer science is the designing and study of algorithms to solve some problem. The first thing that comes to my mind when I hear that statement is, what is an algorithm? Well, an algorithm is a step-by-step method for completing some task. It must be precise, unambiguous, and capable of solving the problem in a finite amount of time. That may sound trivial, but that's actually pretty important. So let's look at an example. Let's say you make a recipe for tres leche cake for someone who has, never really cooked. And you include the step, mix all dry ingredients. Okay, what are the dry ingredients? You've not defined that. So nowhere in the prior steps in this algorithm that you have just written out here do you define what the dry ingredients are. So this would be an ambiguous solution to making tres leche cake. So let's look at what an algorithm might look like to write hello world on a marker board. So instructor tosses dry erase marker to student, student catches the dry erase marker, walks to the dry erase board, takes off the dry erase marker cap, and writes hello world on the dry erase board. Student puts top back on dry erase marker, hands marker to instructor, returns to seat. This list of instructions is precise. There are ambiguities, such as if you wanted to get if you wanted to push it to its extent, what is a student and what is a dry erase marker. But in general, it's not ambiguous, and it can be completed in a finite amount of time. This does not continue for eternity once it has begun. So this would be an algorithm to describe how to write Hello World on a dry erase board. So if that is what an algorithm is, a unambiguous, precise, executable in finite time set of instructions, then what is a computer program? Well, a computer program is just a set of instructions that a computer can follow. So that statement does not necessarily mean that the set of instructions equals an algorithm. It could be that the set of instructions causes the computer to continue to process for infinite time. So in which case, it would break one of our requirements. So computer programs are related to algorithms, but different. So a computer program is a set of instructions that a computer can follow. Software is a collection of programs. So common programs that you have used in everyday life, if you use a Windows computer, then your Windows operating system is a program. That is a software that is a collection of programs that runs on the hardware that is your laptop. The same is true of Mac OS. Mac OS is a computer software that is a collection of programs that runs on the Mac set of hardware. Same for Linux kernel. Probably when you think about computer software, you may or may not think about your operating system. You should think of editors and word processors, Excel, right? Those sort of programs, those were written by someone. Apps and games, Facebook, Snapchat, all these, anything that runs on a phone or a PC is going to be software. They're all programs, and just because you weren't part of the programming team doesn't mean that it wasn't written by a programmer. And it may seem like a massive undertaking. It may seem almost mind-boggling that, what we do in this class could sum up to Excel or Netflix. But that's because it was a large and very talented team of programmers that maybe someday you will be a member of a team very similar to that and doing great things that seem mind-boggling to the next upcoming computer science professionals. But nearly all computer programs follow a basic algorithmic template. That's get the input, do something to it, and produce an output. So this diagram exemplifies what we just said. There's data coming in, processing that occurs, and then an output is generated. So what this diagram is intended to show is that the data which is coming in right now and the program itself have both been input to the computer. So think about this. At some point, let's say this program is the Excel program. So this is Microsoft Excel. Well, somewhere back through the history of Microsoft, they wrote down the set of instructions that makes up Excel, and it's been stored in memory. And then you've downloaded it into your computer. So your computer now holds Excel in its memory. But fundamentally, even though it has been a long time ago, Excel was an input to a computer. Now you're writing things into cells on that computer, in that program. So you go in, you click, that's an input, and it produces the output of putting your cursor into that cell, and you write 5. And you have some formula input so that it doubles and puts the result in the window beside it. So the computer processes the program, which is Excel, and your input, and generates the output, which is 510. So in this way, the data and the program are both considered inputs to the computer, which then the computer processes the program, which is a set of step-by-step instructions which have an effect on the data which produces an output. A question then is, how does the program get into the computer? You can't talk to the computer, you can't Star Trek it, you can't say hello computer and tell it what you want it to do. So instead, we've had to make rules that if you follow the correct syntax, a programmer is able to write down an algorithm in a way that the computer can understand it. That may sound a little funny, but think about that for a minute. So it's a set of rules that a programmer uses to write down an algorithm in such a way that a computer can understand it. So literally, you're speaking the computer's language. Now, every language has its own set of rules. English, Chinese, every traditional spoken language has a set of rules. The same is true of programming languages, and there are many programming languages. In this class, we will focus on Java. Should you continue on to 2201, which is data structures, C++ will be the programming language you will use. So why Java? Well, it's relatively high level. When people say that a programming language is high level, what that means is that Java, when it's read or written, is closer to a spoken language like English than other computer programming languages. So it's relatively easier to understand and write. So there's other high-level programming languages. Specifically, Python is quite high level. Visual Basic is high level. All these are considered high level. Some, in my opinion, more so than others. The computer and computer hardware don't understand high-level languages, though. So what I'm saying here is, in your computer, there's a set of hardware that includes a CPU, and that CPU is what actually executes the individual instructions that a computer is capable of executing at a fundamental level. Well, that processor does not understand Python, it doesn't understand Visual Basic, and it definitely doesn't understand Java. All it understands is binary. It understands combinations of ones and zeros, which is not conducive to programming. No one wants to literally write ones and zeros to attempt to program a computer. So we need these high-level languages, but then there's sort of a disconnect. How does a computer, which needs ones and zeros, how does it understand this higher-level language? And that's where compilers come in. So a compiler is itself a program that translates a high-level language to a low-level language. So we have a program which has been written down in Java, and then we have a Java compiler which takes in the Java code and produces something that is more understandable by the computer. So we have our high-level language in this diagram on the right. It goes into a compiler, and then the compiler generates what is called assembly language, which then goes through an assembler, which then produces machine language. And these terms are pretty important. You're going to hear them over and over in all CS courses. Compiler, even though this says compiler, and assembler. So your Java or whatever language you're using, specifically say C++, is going to go into a compiler, which is going to produce an assembly language representation, which is going to go through an assembler, which is going to produce a machine language representation. And that machine language is typically referred to as object program or object code. So depending on the language that you use, the compiler is going to compile and then assemble different types of files as executables. For instance, if you program in VisualBasic.net, then the compiler is going to compile that into assembly, which is then going to be assembled into a Windows exe file. Great. That's how you get Windows executable files. Well, if you use App Inventor, then it's going to get compiled into an APK, which is runnable on Android devices. So these files can only run on those specific types of machines. So you can't run an APK on a PC. Don't get me wrong, there's emulators and such that can attempt to run those, but natively on the processor you cannot run a object code program which is intended for Android on a PC. Just the processor does not understand the instructions. So then that kind of raises a question. If you're familiar with the idea of Java and why it exists, you may be thinking, yeah, but isn't that the thing about Java is it's supposed to be platform independent. So it doesn't matter if I'm running on a PC or a Mac or a Linux box, it should be able to run on whatever computer architecture I have. You're right. That is the case. Java does not actually compile a program down to object code. So a Java program, when it is written and compiled, it does not get compiled into assembly, and it does not get compiled into object code. Instead, there's something referred to as JDK, the Java Development Kit. When you install IntelliJ, IntelliJ comes with JDK built into it. The Java Development Kit will translate your program into something known as bytecode. So again, these are important keywords. Object code or object program refers to the code that is uniquely runnable on a specific processor. Bytecode is a very low level, similar to machine language, for some hypothetical computer representation that runs on something called a Java virtual machine. So Java gets compiled into bytecode, and bytecode runs on a JVM. And the JVM actually is what then interfaces with the computer hardware to produce the output. This is how Java accomplishes this platform independence. So Java is always translated into bytecode, and then each machine must have a JVM to be able to run the bytecode. So a program is written in Java. Then it goes through the compiler, and out comes bytecode. Okay? But we still need to eventually get to object code. Otherwise, the processor can't do what we want it to do. So how do we go from bytecode to object code? That's exactly what the JDK does. So JDK, what am I doing? JVM. The Java virtual machine. The Java virtual machine produces object code for each individual instruction. So in the slide up here, the JVM is going to be an interpreter that interprets the bytecode into the relevant object code machine instruction. So yes, Java is platform independent, but the way that that's achieved is each individual computer needs to have a JVM installed on it to be able to run a Java bytecode program. So everyone in this class is not merely going to be running Java programs, they're going to be coding in Java. And for that reason, you'll need the JDK compiler, which comes integrated in the integrated development environment we're going to use called IntelliJ. So let's look at the process for going from programming to running. So you, the programmer, are going to type your program into Java, and when you're finished, you are going to issue a command to the compiler to start compiling. So 1, write your code. 2, issue a command for the compiler to work. The compiler is going to translate your Java program into bytecode. So it'll generate bytecode. Once the program is compiled into bytecode, you'll issue a run command to the JVM. The JVM will interpret the bytecode and carry out the instructions on the processor. So there's a pretty important word built in there, which is interpret. That's the job of the JVM. The Java virtual machine interprets the bytecode into machine code for the specific machine on which it is running. So let's look at a simple Java program. First of all, notice the program documentation. So this is the header that tells who wrote it, and this is the standard information that we would expect to see. There's one thing missing, which may or may not, depending on who's grading it, result in some points being taken off. There should be an extra comment right here telling what it does. So in this case, it should say that it prints hello world. So let's look at this program. So first of all, every Java program must have a class, and that class must be named the same as the containing file. So this class is called Hello Java. The file must be named Hello Java. The spelling and the capitalization must match. So we have a public class, Hello Java, and we'll discuss what that means in more detail in a moment. And then every program, every class in Java needs a main method. So this is the class, this is the method. And our main method is going to issue a command which is system.out.println, and then we're giving it the string literal hello world. So then the computer is going to generate this output. And again, the way that happens, so this is a program that's written in Java. You would issue a compile command that gets written into bytecode. The bytecode is then run on the JVM. The JVM, or Java Virtual Machine, will interpret the bytecode into machine code, which tells the processor to write hello world. So let's look quickly again at a more generic program. So at the top you have the comments, which acts as the program documentation. You have the class. So every executable Java program consists of a class. And again, the class name must be consistent with the file name. Then nearly every class will contain a method named main. The main method is the method that is executed when the executable Java class begins to be executed. So a Java program will contain a Java class if it is executable. The class will contain methods. Methods contain statements. So statements are individual commands. And then along with the statements, there may also be comments that are written in to document what a group of statements is intended to accomplish. Let's look at another program. So we have a Java executable program. If it's executable, that means it must contain a class. The class is named hello, and inside that class we have a method called main. So this program is going to print the line hello world. So we have a comment that says it's going to print a friendly message that tells us what the hello world is and what it's doing. And we have another comment here that says it's going to print a blank line and some other stuff. So the first statement that we encounter prints the line hello world. And it's a print line statement, which means it's followed by a carriage return. So it's going to write the words hello world down here, and it's print line, which means at the end of that it's going to return to a new line. All right, well, the next instruction, the next statement, is also a print line with no words included. So we print nothing and then issue a carriage return. The next statement is a print line containing the string literal this program produces. So we have this program produces followed by a new line. Then we have another print line statement which has the string literal 4 lines of output. So it writes 4 lines of output, and then there's a carriage return. So print line prints what's in the contents of the parentheses and a carriage return. Carriage return returns the cursor to the beginning of the next line down. So as we said, system.out.println, it's a statement that prints a line of output on the console. Typically, you'll hear it called different things: println, printline. I like printline. And it is a statement, so it's referred to as a printline statement. So statement is not a flippant term here. It literally means in Java, methods contain statements. So this is a print line statement. At the end of printing whatever is in the argument for the print line, it will issue a carriage return, which returns the cursor to the beginning of the following line. There's a similar method called system.out.print. And it's exactly the same as printline. However, it does not issue a new line after printing. So we'll look at what that looks like in another example program. A helpful note about printline: if you leave the parentheses empty, so you don't give any arguments to the printline method, then it will simply print a blank line of output. So if you needed to leave a space in between something, so you wanted to say hello world, and then you wanted to leave a blank space here, you could do a print line statement which said hello world, and then have a print line statement with nothing in the parentheses to generate a blank line of text and a new line. So let's do a little comprehension check. We have the program above where we have a class called hello, and in that class we have a method called main, and we have 4 statements. So the first statement is a system.out.println, or shorthand, you can just call it a printline statement, that will write hello world, and then a system.out.println, and then a system.out.print, and the following system.out.println. So take a moment and think about what you expect this program to generate. So first of all, it's going to generate hello world, and it's a print line statement, which means it's going to be followed by a new line or carriage return. So, hello world. Now, the next statement is a print line statement with no arguments in the parentheses, which will generate a blank line followed by a carriage return. Okay. Then we have a system.out.print, which will print out this program produces oh, what's this? Okay, so this program produces, and then immediately the next statement begins to print 4 lines of output after it. So it's kind of ironic. No, this program does not produce 4 lines of output. It produces 3 lines of output. And the reason is because this statement is a print statement, which does not generate a new line. So if you don't generate a new line or a carriage return, then the next print statement or print line statement will begin to print wherever the cursor was left. In this case, it was left right here. So when the next print line statement is executed, it prints 4 lines of output, the words 4 lines of output, starting where the cursor was left. And at the end of that statement, the print line will generate a carriage return, which returns the cursor at that point to the next location in the terminal.